the original question is what makes a good treatment. Okay, so we're going to be looking at medications and vaccines and diagnostic tests. All right. Short answer is good science. In fact, very good science. So we need biologists, we need chemists, we need mathematicians and statisticians, we need management and business people, we need communication specialists. You name it. Everybody really is involved in the development. Okay. Why we're going to focus on mathematics and statistics here in particular, and why do we need that? We need algebra because algebra provides relationships between numbers. We need linear algebra. If you don't know what that is, that's okay. We are dealing with matrices and vectors. A sample, that's where our data is located in samples. They're vectors basically. Okay. And the data file is a large matrix. Basically, that's what it is. It's an array of numbers and letters and codes and short answers. That's all information, right? That's all can be stored in a large matrix, and that's how computer systems work today anyway. We need calculus and analysis for accumulated change and rate of change. That's very important. We need logic because of sound reasoning. Okay. Your conclusions better be found in logic, okay. And we need, of course, statistics and probability. Okay. Basically, we want to look at likelihood of something happening and relationship between variables at a population level based. Once we have the sample data, right, then we start drawing inferences for the whole population. That's where statistics comes in. Remember these two simple equations, okay? They're very powerful. They are simple, okay, but they do have some very powerful implications. Okay. Everybody has seen those, I assume. It's basic algebra. It's okay if you haven't, but I assume you have. Okay. We need to talk just briefly about study designs in general. There are two basic kinds: observational studies and experimental studies. Okay. We'll be focusing on experimental studies for the most part. Research questions involve prevention and treatment. They need to be ethical and feasible. I mean, you need to have human and financial resources to conduct these experimental studies because they are very long and they're very expensive, usually, okay, for the most part. Observational studies are kind of mimicking the experimental study when you don't have enough money, okay, or time, or something is not quite ethical about what you would like to do in an experimental study. Okay. Experimental studies are mostly prospective, but observationals could be either way, retrospective or prospective. Okay. Phases. Okay, so we're going to focus on experimental studies. Phases. Okay, so these studies are very complex. Okay, they take a long time, months, sometimes even years. Okay, just depends on what you're trying to do. Oops. And we have several phases. These are the basic phases that most experimental studies have. You have preclinical or laboratory study, and then you go through from phase 1 through phase 4. Now, some studies can have more than 4 basic phases, and some can have fewer than 4. It just depends, again, on what you are trying to do. But this is a classical example. Yeah, you should have 1 preclinical and then 4 basic phases. Okay. Preclinical studies are mostly cell studies and animal studies, right? To see whether your thing that chemists and biologists developed would even work at a cellular basis or among animals. Okay. Animal studies are a little bit controversial. Okay, there's a lot of controversy about that. Okay, and some companies, pharmaceutical companies, are trying to stay away from that if they can. Okay. But yeah, there is a lot of, we can spend a whole week talking about animal studies, and okay, so we're not going to do that, but anyway. But that's your preclinical phase. Okay. Phase 1, we have to determine if what we have developed, assuming that the preclinical study is done, We passed that stage. We are moving on to phase 1, usually with a very small group of people. We're going to study some basic properties of the treatment, okay? And it can be used to study possible side effects right at that stage. Toxicity and food interaction, okay? Interaction with other treatments or supplements, for example, right? That's always very important. Your goal is to determine the maximum tolerated dose at this point. Okay. Phase 2. What is the potential clinical efficacy, all right? And describe the short-term incidence of side effects, if there are any, and there usually are some. There will always be some, okay? Okay. Determine a different dose for different kinds of cases. Okay, we can have a mild, moderate, or severe case of a particular disease. We need to know what is the maximum dose in each case. If we are concerned about the difference between children and adults, that's another thing that we need to study. Okay. A different dose for children than adults. You've seen that before, right? It's not the same. Okay. So this phase will determine whether the new treatment is going to be useful or not. So if I determine here that, this is not that good, I need to terminate my study right away so that we don't waste time and money anymore. Okay. So it's okay, right? There are a lot of clinical trials that stop at phase 1 or phase 2, right? They're abandoned. So things didn't go according to the plan. You better stop for whatever reason. Remember, you have to be ethical, right? Nobody needs to be or should be hurt intentionally. Okay. So that's something to watch out. Phase 3 is where things get complicated, okay? Because now you're going to start recruiting a much larger group of participants, usually between 300 and 1,000, but sometimes much more than that, many more than that, okay? We're going to randomize participants to two groups, treatment and control. Your control group can either receive placebo or the existing regimen, okay? Either way, depends on how you want to set that up. This phase should provide compelling or strong evidence that the new treatment is useful or not useful. Okay? You as a researcher, you hope it's going to be useful, okay? But sometimes it can happen that it's not, okay? And then that's where you would stop. This phase is a must in order to obtain the license to, or meet your standards. Okay? And results and application must be submitted to the Food and Drug Administration. Okay? That's usually several thousands of pages. Okay? Somebody needs to write that. Okay? We usually have a group of 50 to 100 people who are writing these reports. Okay? You have to be good at technical writing. Okay? Based on the evidence that you present, you have to write your report. Okay. That's a lengthy process. Okay. Somebody's got to do it. Right? So if you're good at writing, that's where you would step in. Okay. But you have to understand what's going on at the same time. Okay. Phase 4. This is usually what happens after the drug is approved and it's on the market. Now we're going to follow for a few months or maybe a year or two and see what's happening, okay, in the general population for people who are taking this new treatment or drug. Okay. So we're going to monitor the effects and side effects. In cases of any reported adverse reactions, we'll have to step in and file separate reports. Okay. We may even have to withdraw the treatment from the market. The government may require that. If we don't, what happens? You pay huge fines if you don't follow the rules. Okay? I mean, huge fines. In tens and hundreds of millions of dollars. Okay? This is not a joke. So this is an important phase. And it's usually done as an observational study. You simply follow people through time and see who's taking the new drug versus who's not and see what's going on. long term. So what we use in phase 3 is the randomized clinical trial most often, and this is the simplest kind. As we said, we're going to start with our population of interest, our participants. Okay, we're going to divide them into 2 groups, randomized. The participants themselves don't know which group they're in. And the scientists who are collecting data, they don't know who's in which group. Okay, we call that double-blinded kind of clinical trial, so in order to avoid any sort of personal biases. Okay. So everything's kind of kept secret until the end. Okay, until the end. And then, of course, we're going to be looking for the outcomes, whatever the outcome is that we are looking for. Okay, the outcome is the present or absent. Okay, 2 things can happen. Okay, same in the comparison or control group. Okay. Did we get what we wanted or not? Okay, we're going to record that. We're going to see what happens. Okay. So individuals are randomly assigned to 2 groups. Okay, they are prospective in nature, and they can take a lot of time. Okay, several months, in many cases even years. Okay. The randomization today include computer random number generator. Okay, that's what we use today. Using flipping a coin, we don't use that anymore. Okay, although one can do that. It's just not considered the best thing to do anymore because we do have wonderful technology that can assign people randomly into 2 groups. Okay. And usually there's a central office that handles randomization and stores and manages the data. Okay. So, as I said, a lot of people are involved in conducting clinical trials, a lot. Okay. They may not be all in the same place either. Especially today because we transfer data electronically now all the time, so things go much more smoothly than in the past. So we need to talk a little bit about probability and odds, okay? Because we want to focus on mathematics and statistics. Okay? Probability is a measure of likelihood that an event will occur. So it's the ratio of the number of outcomes in the event divided by the total number of outcomes under consideration. Okay. Usually expressed as a percentage or relative frequency. Okay. Odds in favor of an event is defined as the number of favorable outcomes divided by the number of unfavorable outcomes. Okay. Usually expressed left as a ratio. Okay. I'm going to provide a couple of examples here so that you get an idea of what I mean here. A very simple example, draw 1 card at random from your standard well-shuffled deck of cards. Okay. What is the probability of drawing an ace? 4 out of 52. You have 4 aces and you have 52 cards. That's your probability. Okay. Is it likely to happen? No. Can it happen? Yes. Probability does not predict future. Okay. Be careful with that. It just tells you how likely is something to occur. That's it. You still don't know whether it was going to happen or not. That's it. The odds in favor of getting an ace, it's just 4 out of 48. I have 4 aces, and then I have 48 cards that are not aces. That's the odds. Right? So it's 4 to 48 or 1 to 12. So it's a little different, okay? It's not the same as probability. They are related, but they're not the same. The probability of drawing a red card, it's 50%, right? 26 out of 52. But the odds is 1 to 1. Okay? Because it's going to be 26 out of 26. Right? I have 26 cards, and red cards, and 26 black cards, so that's it. Okay, so summarizing data is the important part of describing what's going to happen in our case. So, say you're in phase 3 here. We can summarize our data in this way because this is what we are interested in. We're going to look at first column where the treatment was effective. We're going to record how many did we have in the treatment group and how many in the control group. Okay. Their total is A plus C. The treatment was not effective. Okay, that'll be B plus D, right, in both groups. And then, of course, your totals, right, have to add up to your sample size overall. How many people did you have in this study? Okay. It looks simple enough. It looks simple enough, but the data set itself looks much more complicated. Okay, this is just a summary, right, of what we look at. Okay. For tests, for example, for screening tests or diagnostic tests, this is very important. One column will be tested positive, one tested negative. The disease is present, that's your true positive, right? Your false negative. Yeah? You tested negative, but you do have the disease, right? We call that false negative. Okay? Same thing in the second row. You have disease is absent, but you tested positive, that's a false positive. Okay? And tested negative, that's true negative, right? That's what you have there. And once again, you're adding totals horizontally and vertically, right? To get the grand total in your sample. Are we okay so far? Okay. We hope, right, in these diagnostics tests, we hope that the true positives and true negatives will dominate the table. Okay. We expect biggest numbers in those two cells. We hope. If it is a good screening test. All right. Two most important measures of risk or association are, the first one is the sample risk ratio, is the probability, is the ratio of two probabilities, is the probability of outcome in the treatment group divided by the probability for that same outcome in the control group. So what we have to divide in the numerator, right, we're going to have A over A plus B. That's right here, A over A plus B. And then probability for the outcome in the control group will be C over C plus D. Okay, if you look back here, that will be C over the total C plus D. Those are the two probabilities, right, for the two groups. For the outcome of interest. Okay, that's why you see A and C in the numerator of both the numerator and the denominator. Sample odds ratio, now we move to the odds. It's the odds for the outcome in the treatment group divided by the odds for that same outcome in the control group. But this is now different, right? Now we have to divide A over B. It's the number of favorable outcomes divided by the number of unfavorable outcomes. Okay. A over B, right? Treatment was not effective. That's an unfavorable outcome, right? So that's why we have A divided by B, and then in the denominator we have C divided by D. And that's what we get here, right? Simplify that a little bit by cross-multiplying. You're going to get AD divided by BC. You just basically cross-multiply in that 2 by 2 table. Right? A times D divided by C times B. Okay. Are we okay? Sure. All right. Complex fractions, right? Okay. We love those kind of things. When the risk ratio, the odds ratio is equal to 1, i.e. numerator is the same as the denominator. Remember, we're doing with fractions. That simply means there is no association between the treatment and outcome. Okay. Because you're basically saying the outcome is the same in both groups. So this new treatment is not really all that, it's not effective. I mean, it's not doing anything. It's just as good as placebo, or it's just as good as the previous older treatment, so it doesn't really affect anything. So that's the number researchers are trying to stay away from. Okay? Try to stay away from 1 as much as possible, because that simply tells you, okay, you're not getting what you're supposed to be getting. You better stop your experiment. You're done. Okay. When the risk ratio and the odds ratio is greater than 1, then you have what we call positive association. Okay? And finally, when it's less than 1, you have a negative association. And sometimes people are looking for that as well. We're going to see an example when you're actually looking for that number to be less than 1. Because you want a reduced risk for something bad to happen in the end. Really quickly here, the risk ratio is used in both experimental and observational studies, but the odds ratio is primarily used in observational and retrospective studies, actually. So that's a little bit more complicated to explain, so I'm not going to go into that right now. But anyway, that's just something that researchers keep in mind to know which measure to use. Okay. So here's the first example. Okay, we developed a new treatment to reduce cholesterol. Okay. And we summarize the data. We have received from our management office, so the data was recorded, it was uploaded, and it was sent to us. We can now summarize this, and this is what we get. We have two groups, okay, and the old treatment, that's your control group, right? So we now compare how good is this new treatment, right, in comparison to the old treatment. Okay. And this is what we got. Okay. So let's get the sample risk ratio. It'll be 645 divided by 800, okay, divided by 455 divided by 710, because it's the ratio of two probabilities. And it turns out to be 1.258. Once I simplify everything right across, multiply 645 times 710 divided by whatever 455 by times 800, and I get 1.258. It's a very modest result. It's not a bad result, but it could be better in any case. But what does it mean? It means that people who receive this new treatment were 1.258 times more likely than those who got the old treatment, right, to show a clinically significant reduction in serum cholesterol. So that's a pretty good result. It could be better, as I said, but it's not bad. It's not bad. If we made a comparison with the placebo, for example, you could argue that this is not that great. It's just a little bit better than placebo. But since this was a comparison with the older drug, it's okay. It's okay. Maybe it's a little bit of improvement. So the management in the company will decide whether we want to proceed with this or not. Okay. Or maybe you have to go back and improve the formula, okay, somehow. Okay. Next is the new treatment safe, for example. Okay, that's another thing we have to look at. Serious side effects, okay, and no serious side effects here. Again, right, with respect to two groups. Okay. We can do odds ratio here because this is usually done in phase 4, right, after the drug has already been on the market for some time, and we are following long term, for example, what's happening. Well, what do we observe in the new treatment? Right, we have a pretty high number of serious side effects, right, compared to the previous treatment. Right? So we'll have to divide 200 by 600, right, divided by 300 by 680. Because we are doing the odds ratio. And the odds ratio turns out to be, that's considered a very high number, 7.556. Oh, that means that if you are receiving this new drug, you are approximately 7.556 times more likely than those who are getting the old treatment to experience serious side effects. So, if you, right, don't do anything about it, the government will, okay, because these reports will be sent to the government right away. Okay. All the clinics and hospitals, they have to file these reports on a daily basis. Okay, and the government will see this is happening and you're not doing anything about it, you're going to get in serious trouble. Okay. Would you recommend withdrawing this drug from the market? Yeah, I would, for sure. Okay. This is way too high a number. The drug may be effective in reducing cholesterol, but we have way too many serious side effects. The proportion of people who are experiencing the side effects is way too high. And maybe it's time to then withdraw this drug from the market, right? Okay. So this is what we mentioned a little bit earlier, right? This is all based on samples. Now we have to make inferences what will happen in the general population, right? And this is where statistics come into play. And what we talk about here is the confidence intervals for both the risk ratio and the odds ratio. And of course, this is where, if you like, calculus, right? This is where that comes into play, and you need some heavy-duty calculus to derive these formulas. Okay, this is kind of fun, but I'm not going to go into that. Thank God for that. But anyway, yeah, you have a bunch of logarithms, right? Logarithms are very, very important. Okay, don't underestimate the power of logarithms. They are everywhere. Okay, you just don't see them. Okay, that's a different story. But this is for the risk ratio, and then this is for the odds ratio. This is how you calculate these things. But in real life, people don't use these formulas. They use computers that have everything built up in their algorithms, so that you can get the range for the actual population risk ratio. In our example, remember our sample risk ratio was 1.258, and the actual range is 1.1792 to 1.342. That's good. I'm safe. I'm safe because 1 is not included in this confidence interval. Remember, 1 is the bad value. I don't want to see 1 in my confidence intervals, okay? Because that will tell me there is no association between what you are doing and what's happening out in real life. For the odds ratio, remember our result was, what was it? 7.556. The confidence interval is 5.069 up to 11.26. And that's a result that I would worry about quite a bit. Okay, so the risk for developing your adverse or serious side effects is actually pretty high, on the high end here. Right, it could be as high as 11.26. It could be as low as 5. Even this is still pretty high. So anyway. Okay, flu vaccine. Okay, flu vaccine. So this is an example where your risk ratio, you would want that to be less than 1. Okay, so we have people who got the flu and people who did not get the flu, people who were vaccinated and people who were not vaccinated. Right? And I want to see how effective my flu vaccine really is. Risk ratio, it'll be what? It'll be 56. 56 out of 434 divided by 100 out of 420. Right? I need 2 probabilities, right? Okay, so that's what I got. 0.542. Okay. Okay, 0.542. So the vaccinated individuals were 45.8% less likely than non-vaccinated individuals to contract the flu. So that's good. That's good because the risk for actually getting the flu went down, right? If I got vaccinated. Okay. Now, we have to be careful when the number here for the risk ratio is less than 1. To get the actual reduction in risk, you have to subtract from 1, okay? Because your risk ratio in the exposed group is 0.542 of the risk in the unexposed group. So to calculate the reduction in risk, you simply subtract, which you don't do when your risk ratio is more than 1. Okay. You don't do that, but anyway, in this case you do. All right, screening tests. All right, so we are trying to develop a new screening test for COVID-19. I'm gonna gather some people who I know already. I know whether they have the disease or not, and I'm gonna apply my new test and see what happens. Okay, I'm gonna have a bunch of true positives and true negatives. I'm hoping, as I said earlier, these numbers are gonna be the greatest in my table, and I'm gonna have some false negatives and false positives. Okay. So what we do with these tests, we do things a little bit differently. The first one is to look at the sensitivity or the true positive rate. It's simply the proportion of the diseased individuals who actually tested positive. So what am I going to have in the numerator? Right? True positives and false negatives. Those are the people who actually do have the disease. Okay, and then in the numerator, I'm going to put true positives. Okay, so that's my basically true positive rate or TPR or sensitivity, right? We would like this number to be at least 80% hopefully more than that. But in this case, it turned out to be 83.58. So 83.58% of all the diseased individuals tested positive. Okay. Not a bad result, right? Pretty good. Next one is the positive predictive value, or PPV. It's the proportion of those who actually tested positive who have the disease. So in the denominator, right, my denominator is going to be a little bit different now. I'm going to have true positives and false positives, because it's the proportion out of all of those who tested positive. So there are two possibilities, right? And then true positives in the numerator. And that one will turn out to be 0.9271. So 92.71% of those who tested positives actually have this disease. Good result too. It's over 90%. That's good. That's considered pretty good. Next one is specificity, or the true negative rate. What are we going to do now? It's the proportion of non-diseased individuals, so it's false positives and true negatives. Those are the people who do not have the disease. Okay. And in the numerator, well, who tested negative? Okay. That's an excellent number, 95.04%, i.e. 95.04% of non-diseased individuals tested negative. So that's what happens with some of these tests, right? They're more reliable if the outcome is negative, or they could be more reliable if the test is positive. In some cases, if you tested positive, maybe some additional tests may have to be performed, right, to make sure. Sometimes that can happen. Okay. But you wouldn't want this number to be like, say, 0.31 or something like that. Okay, that's pretty unreliable. That would not be a good thing to have here. Negative predictive value, or NPV, is the proportion of those with a negative test who are not diseased. So non-diseased. Okay, so we have false negatives and true negatives in the denominator, and then who actually tested negative? 88.46, that's not bad. That means that 88.46% of those who tested negative do not have COVID-19. It's pretty good. That's a decent result as well. Overall accuracy is just the proportion of true positives and true negatives. We would like this number to be at least 90%. Okay, overall accuracy, I want that number to be high. Okay, if this number is like 70 or 60 or 50%, forget it. You're not doing your job right. Okay, your chemists and biologists are not developing this test correctly. Okay. So, and by the way, should you ever have to see a specialist for some disease and you have to get tested, that specialist better know something about specificity and sensitivity and these predictive values. Okay, you should ask, because that's how you are testing whether this specialist really knows what he or she's talking about. Okay, ask just out of curiosity if they know. If they don't know right away, they should know where to get those numbers by immediately. Just in case, right? If you need to get tested for any kind of disease, whether chronic or infectious, it doesn't matter. A specialist should know. And here's a range that's usually followed for the overall accuracy. Yeah, you wanna do it be at least at 0.8, okay, so that your test is very good to excellent. This is really what we should be dealing with. Anything below that. It's not really considered a good thing to go, right? I wouldn't even consider this 0.6 to 0.7. Yeah, it's sufficient, but it's not a good thing to use. Okay. False positive rate. Okay. That's the proportion of non-diseased individuals who tested positive. So we have false positives in the numerator, right? And we have false positives and true negatives in the denominator. Okay. And we would like this number to be small, very, very small, preferably under 5%. Okay. Some people would say under 10%, but anyway. So what does that mean? That means that 4.96% of the non-diseased individuals actually tested positive, right? Keep that number small, okay, as small as possible. Okay. If you can get that, right? False negative rate, very similarly, it's false negatives divided by what? True positives and false negatives, right? So it's the proportion of the diseased individuals who actually tested negative. Okay. That number also should be small. Here it's a little bit high. It's a little bit high, 16.42%. A little high. And then we get into the likelihood ratios. LR plus is the ratio of the true positive rate to the false positive rate. Okay, our number turned out to be, so we already calculated these numbers, and we divide and see, oh, okay. What does that mean? That means that true positive is approximately 16.85 times more likely than false positives. So that's pretty good. Okay, that's pretty good. Negative likelihood ratio, very similarly, it's going to be the ratio of the false negative rate to the true negative rate. We would like this number to be also pretty small. Okay. In our case, it turned out to be 1737. So false negatives, right, because they're in the numerator, are 82.63%, less likely than true negatives. Okay. This one is actually kind of a little bit different, right? If you look at the positive likelihood ratio, had the true positive rate over false positive rate, but this one has a false negative rate in the numerator and the true negative rate in the denominator. Okay. That's done on purpose because of something else that's going to come up in a minute. Okay. And this is it. It's the diagnostic odds ratio, or DOR. Okay. It's just the ratio. It's the ratio of the positive likelihood ratio and the negative likelihood ratio. Okay. In our case, it's 97 approximately, and we want this number to definitely be more than 1, preferably more than 10 or 20. It doesn't have a particular interpretation, but when people who are developing this stuff and they're looking at this number, they focus on this number. Oh, okay, it's at least 20. Okay, we're doing good. Okay. The higher the DOR, the better the test performance. Okay, basically that's what they're looking at. Like if this is like 100 or 200, oh, they'll be really happy. Okay. You don't want this number to be below 1 for sure. You're not doing something right. Or you messed up your number somewhere along the line. Okay. Whatever. So that's another one. Yeah, division by 0 could be tricky, right? We cannot divide by 0, as you probably learned in algebra, right? So when the number of false positives or the number of false negatives is 0, i.e. a perfect diagnostic test, the DOR cannot be calculated. We're going to end up with 0 over 0 right there. That could be an issue, right? It is an issue. It's not just could be. And then we can use a correction factor, right? So in order to avoid 0, people just put 0.5 in those 0 cells so that you can still actually get the DOR if you need that. But that rarely happens. Okay. We don't need to be worried about that. But anyway, just an interesting mathematical point here, right? Watch out for the zeros, right, in those cells. Stratification may be sometimes also needed in these clinical trials. You may stratify according to age, because you are interested in what happens in individuals under, say, 55. I just arbitrarily took 55, and those who are at least 55. Okay. For some reason, you're interested in that. There's something that needs to be studied carefully, and then you would, of course, do your randomization in both of these two groups. Okay. So it gets more complicated, right? You can have more than 2 groups, okay, or 2 levels of study. In any case, how are we doing on time? I'm not really sure. How is it?
42.
Okay, good. So here's an interesting exercise, right? So if you want to do this exercise, just email me, right? I'll send you the numbers. Can you show that sensitivity and specificity do not depend on the prevalence of the disease? The predictive values do. Okay, and that's why in diagnostic tests, people prefer sensitivity and specificity, because they don't actually depend on the prevalence of the disease. The prevalence, how is the prevalence defined? Well, it's the true positives and false negatives. Those are the people who actually have the disease. Right? They either tested positive or they falsely tested negative, but they have the disease, divided by the whole sample size. And here's the hint. Here are the 3 different scenarios, right, in 3 different colors, right? In all these 3 cases, the prevalence is different, but the sensitivity and specificity stay the same. They're actually the same in all these 3 cases: yellow, orange, and blue. So that's interesting, right? That's why in these diagnostic tests we prefer sensitivity and specificity rather than predictive values, although both are used and both should be presented as such. It's an interesting exercise. If you have any questions, you can email me. And I have a bunch of online calculators that will calculate for you sensitivity, specificity, predictive values, risk ratios, odds ratios, all the things that you want and don't want. I mean, it's amazing. Everything is nowadays online, and you can quickly get these values and the associated confidence intervals, right, to make sure that one is not included in there, stuff like that. If we have time, I can maybe look at one of these and see. Oh, where are we? Maybe here. Okay. So here we go, right? We would enter some number for, let's see, true positives and false. Oh, okay, I don't know. What numbers do you like? I don't know. False positives, so small number, like maybe 12. Okay. False negatives, 15. Okay. True negatives, let's see, 345. Okay. Let's see if we can get some numbers out of here. And there we go. Oh, that's pretty good. The results are pretty big. I purposefully put small false results. Okay, they're not that bad. All right. Whoops. I cannot do this. All right. But anyway, we are right here. So yeah, you can see the sensitivity is pretty high, and you get the confidence interval for it right away. Specificity is pretty high. Positive likelihood ratio is really good. Negative is where it should be. And the predictive values are really impressive. Okay, that's because I purposefully, as I said, put small numbers in the false positives and false negatives.
How confident are you with the new push to get a COVID vaccine?
I'm pretty confident. I don't know when it's going to happen, but yeah, they're rushing a lot. But they're careful as they're rushing as well. Yeah. Because remember, there was an instance was it in August when somebody got sick in the treatment group, so they had to stop for a few weeks or maybe a few days, I think it was, to see why did this person develop some serious side effects, and then they continued, right, without that person.
Without that person.
Sometimes you have to do that while the clinical trial is going on, when that kind of stuff happens, because you want to examine. Luckily, this was just one person. If it was more than one, then yeah, it'd be a much different story. So hopefully we'll have the vaccine soon. I mean, I don't want to predict anything, because people get sensitive and political about it, so I'm going to stay away from that. But yeah, I think they're doing their best that they can. They're working day and night, so and a lot of people too are involved in this. So it will happen. We just have to be, patient.
You're not patient.
I know. No, nobody is. We are all getting tired of these masks and everything else. But one day, well, hopefully very soon. What now?
If the vaccine comes out under these rush conditions, would you take it?
Yeah, I probably would. Yeah, I would probably want to read about it a little bit. Because there will be some peer-reviewed articles published about it right as soon as it happens, and then I would examine those very carefully. But yeah, I would know it.
HBO